Okay, so systems with general process and interarrival times. So again, we are dropping the condition of having exponential processing times that follow an exponential distribution, and also interarrival times that follow a exponential distribution, which makes our analysis very simple in terms of the MM1Q. So without the memoryless property of the exponential distribution, which facilitates our analysis, we cannot compute exact performance measures for the G1Q. However, we can estimate them by the means of the two-moment approximation, basically the variance, which makes use of only the mean and the standard deviation. Or the coefficient of variance of both the interarrival times and the processing times. So as we did for the MM1 case, we will proceed by first developing an expression for the waiting time. In Q, or CTQ, and then compute the other performance measurements. Okay, so it's the same process that we follow for the MM1, but now dropping the assumption that we are going to have exponential arrival times and exponential processing times. Okay, so on the next slide, I have the formula for computing the cycle time in Q. Again, this can be split in three different components: the variability, the utilization, and the time processing. So our expression will use the coefficient of variance, or the square coefficient of variance for the arrivals, and the square coefficient of variance of the effective processing time as part of the variability part of the equation. So this is a useful model for a single machine workstation. Okay, so this applies only for a single machine. Separate terms for variability, utilization, and processing time, as I mentioned already. And CTQ increases with the coefficient, or the square coefficient of variance of both the arrivals and the effective processing time. So if those variability coefficients are high, that means that your cycle time in Q is going to be high as well. Okay? So this is again separated into three areas: a dimensionless variability, variability term, we also have a utilization term, U, and we have the time term. Chart, what I'm trying to show here at the top. And again, looking at the equation myself, you can see that variability will cause the congestion. So the higher the variability, the higher those two coefficients over there, and the higher the cycle time you're going to have in your Q. Okay, so now we can go and look at one of the examples that is presented in your textbook for this specific type of problem. So if we go back to the Breyer patch manufacturing example and consider the machine X19, recall that this machine has a high variability, so the square coefficient of effective processing time was 6.25. Again, assume the time between job arrivals is exponential, so we're going to have a square coefficient of variance for the arrivals equals 1. And the utilization of this machine is 0.95, so it has a very high utilization. So we can compute or we can use the VUT equation to compute the expected queue time for this machine. So again, what we're going to do is just to apply the same equation that we just discussed. So CTQ is going to be equal to the square coefficient of variance of the arrivals plus the square coefficient of variance of the effective processing time divided by 2 times the utilization divided by 1 minus the utilization times the effective processing time. So in this case, we know that CA squared is 1, CE squared is 6.25, all that divided by 2, times, we know the utilization, 0.95, so it's 0.9583 divided by 1 minus that amount. And then the effective processing time is 20. So this is going to be equal to 1.67 minutes. I'm sorry, 1,667 minutes. Which is about 27.79 hours. So one thing that I observed in the homework that was submitted last week is that some of you are not being consistent with the time units. So sometimes the information that is presented is in terms of hours, and part of the information is presented in minutes. So you need to make sure that you're consistent when you're computing your performance measurements. So you are using the right units. Okay, so now suppose that the X19 fits the Tortuous 2000. Okay, so now we have a series of machines. First the X19, then the second machine, the Tortuous 2000. There is no yield loss, so the rate into the 2000 machine is the same as the into the X19. And since the two machines have the same effective rate, they will have the same utilization. Okay, so again, very high utilization, 0.9583. However, to use the VUT equation, we must find the arrival or the coefficient of variation of the arrival process to the tortuous. We do this by first finding the departure coefficient of variance from the here, X19, or the CD by using the linking equation 8.10 in your textbook, but this equation was given in the first part of this lecture, and the equation is as follows. So it's CD equals the effective coefficient, the square coefficient of variance of the effective processing time times the utilization square plus the square coefficient of variance of the arrival process times 1 minus U squared. Okay, so this equation, we discussed this equation on the first part of this second lecture. So I'm bringing that equation back here, and I'm using that to find the square coefficient of variance of the departures from X19. Okay, so that will be, so for example, we have X19 here, and then we have the 2000 machine here. So what I'm trying to find out is what is that coefficient of variance of the departure, because that is going to be related to my coefficient of variance of the arrivals to this 2000 machine. Okay, so for this one, we know the values of all these parameters. So this is 6.25 times 0.95 83 squared plus 1 times 1 minus the utilization, which is 0.9583 squared, and this is 5.8260. Okay, so again, what we're trying to find now is the CPQ for the second machine. Okay, so we have the coefficient, the square coefficient of variance for the departures of X19, and that's going to be the same as the square coefficient of variance of the arrivals at this machine. Okay, so if we want to compute CPQ for the second machine, now we need to use this as our CA square. What's what we are going to do next. Okay, so since the here X19 fits the 2000 machine, the square coefficient of variance of the arrival process for the Tortuous 2000 is equal to this square coefficient of variance of the departures of X19. Okay, so the expected Q time for this second machine will be the following. So we're going to use the same equation. CTQ is going to be equal to CA squared plus CE squared divided by 2 times U divided by 1 minus U TE. So this is the 5.82 that we just compute plus 1 divided by 2 times 0.9583, 1 minus 0.9583 times 20, and that is equal to 1,568.97 minutes, which is about 26.15 hours. Okay, so 26.15, 27.79. So they have about the same cycle time in Q, even though when you look at those CA values, you see that for the second machine is much higher than for the first machine. Because the first machine is 1, the second machine is 5.82. So I'm going to make a note here. So notice that the Q time at the Tortoise 2000 is almost as large as for the here X19, even though the X19 has much higher process variability. So the excess time and congestion is a consequence of the propagation of the variability from upstream activity. Okay, so this discussion again applies for machines that have, or for stations that has only one machine. In this particular example, is looking at those stations with only one machine that are located in a series. So you know that the departure process is going to be affecting the arrival process of the next machine. There's another type of analysis that looks at the CTQ when you have parallel machines. So that means that instead of having a station, so let's say this is what I call the station, those dotted lines are representing the stations. So far we are looking at an example that has one machine per station. Okay, but there will be cases such as the one that we saw in the lab, in which you're going to have multiple stations. Let's say you have two, and they have the same processing time. So the analysis for those type of systems is going to be different. So if you want to compute the cycle time in Q for such cases, then the formula will change. Right? Specifically, the type of the utilization part of the equation will change, which is what I'm presenting here. So this is a useful model for multi-machine workstations. It's extremely general, fast and accurate, and easily to implement it in a spreadsheet. Okay, so I'm not going to be asking you to solve something like this by hand. Especially, you shouldn't expect something like this in the exam. But I want you to understand that can also be a tool that you can use for analyzing systems in which you have parallel machines. The assumption here that you need to remember is that when you say you have parallel machines and you're trying to implement this type of analysis, is that you're assuming that both of the machines will behave in the same way, meaning that it will take the same time for them to process a part, which was the same assumption that we did for our model in the lab. We're assuming that we have two cashiers and both of them were behaving in the same way, meaning that they were taking the same time to serve the customers. And also the cookers. So the cookers were taking the same time to process the orders. Okay, so that's for parallel machines, so parallel workers. Okay, so now we need to look at what are the effects of blocking in our analysis. So sometimes you're going to have certain type of limitation in your queues or your buffers, so you don't have enough space to keep as many units. And also we noticed that in our lab, so we had a specific capacity for our queue, and if you were above that capacity, then you were bulking those items or those customers. Okay, so the BUT equation that we discussed characterizes stations with infinite space for queuing. So again, no capacity limitation for, you can have as many items as you want between stations or at the beginning of the stations. This is useful for seeing what happened to the working process and the cycle time without restrictions. But real-world systems often constrains this width. So you're going to have a buffer and it will hold this many units. So physical constraints such as space or spoilage, or logical constraints such as Kanbans. So Kanban systems are related to the just-in-time philosophy implemented by Toyota. So these are this is a system that uses cards, different colors of cards around the stations, and those are basically used to define if you need to restock your station or not. Okay, so it's basically constraining the number of units that you will have waiting in your station. So if you notice that the parts that you are using, you're getting out of stock, you will change the car color and someone is going to bring a new car with more parts. Okay, so those are the logical constraints. The blocking models estimate the working process and the throughput for a given set of rates and buffer sizes. Much more complex than non-blocking open models and often require simulation to evaluate realistic systems. So that's why looking at the simulation modeling at the same time that we are doing this analysis is very important, because sometimes, especially when you get to the non-blocking, the blocking models, it gets very complicated to be able to do that analysis by just looking at the equations. So that's why you need the simulation modeling technique. Okay, so you're seeing both in this class, which is good. The MM1Q, but there is only enough space for B units in the system. So that's the notation that we are going to use to basically illustrate that we're going to have a buffer capacity for our system, and that is what corresponds to the M1B notation. The arrival rate, R8, takes on a different meaning than it does in models with unbounded queues. Now it represents the rate of potential arrivals, assuming that the system is not full. Okay, so U, or the utilization, RA times T, is no longer the long run probability that the machine is busy, but instead represents what the utilization will be if no arrivals were turned away. Okay, so remember now you have a buffer, and at some point if you fill that buffer, you will not be able to put more entities there. Okay, so the arrival rate now has a different meaning. It's going to be looking at what will be the arrival rate when you have space, basically. And the utilization now is going to also have a different meaning. So consequently, U can equal or exceed 1 for this particular case. So for the case where U is different than 1, the average width and the throughput are computed using these two equations. And for the case in which U equals 1, then the width and the throughput will be computed using these equations. Okay, and you don't have to memorize these equations. What I would recommend you to do in order to get ready for the exam is that you start putting all these equations in a paper. Going to allow you to bring the formula sheet. Most likely, it's going to be a one page for both sides, so you can use the space to put all these formulas. But that's my recommendation. Okay, so For either case, we can use Littl's law to compute the cycle time, Q time, and Q length as follows. So these are the same equations. Cycle time is width divided by throughput. The cycle time in Q is now using the cycle time minus the effective time. And the width in Q is the throughput times the cycle time in Q. Okay, on the next slide we have as an example, very simple example, an MM1BQ. Okay, so we have an infinite number of raw materials coming in, and we have B buffer spaces. So you see we have 4 spaces here that are the ones that are allowed to come in to the next station, because that's the only space that we have. So there's room for B equals B plus 2 jobs in system. B is the buffer and 1 at each station. So for model of station number 2, we have these equations. So this goes to U divided by 1 minus U as B gets closer to infinite. So again, you're getting closer to the previous system or the initial system that assumed that you don't have a capacity limitation. And it is always less than the width for Mn1. The throughput goes to Ra as B goes to infinite, always less than the throughput for Mn1. And then we have the little laws for U equals T times 2, or T of 2 divided by T of 1. Notice that U1 greater or U greater than 1 is possible, and formulas are only valid for U different than 1, as we discussed on the previous slide. So let's look at this example. So here we have T of 1 is 21 units, T of 2 is 20, we have a buffer equals 2. So we can compute the utilization for or U for this system divided by these two numbers, and that's 0.9524. The width of MM1 is going to be equal to 1 to U divided by 1 minus U, and that's equal to 20 jobs. And the throughput of MM1 equals the arrival rate, which is going to be 1 divided by T of 1, and that's 0.00476 jobs per minute. Okay, so this is the analysis without taking into consideration the finite buffer. Okay, so here we have a unlimited buffer, but when we have a finite buffer, now we can see how the things are going to change. So the throughput now is computed using 1 minus U, the power of B, which is the buffer, divided by this times Ra. And as you can see now, the number of jobs per minute is 0.39 jobs per minute, which is 18% less than with the unlimited buffer. And in terms of the width, since now we have some buffer limitation, we should expect that width to go down. So that width is going to be equal to 1.8954 jobs. And it went from 20 to 1.89, so it's 90% less width. Okay, so it does make a difference. Maybe if you look at the number of jobs being processed, 18% might not be a large number. So by controlling the buffer, you are not losing, you are losing almost 1/5 of your production. So it will make a difference depending on your company goals. So in terms of seeking out for variability, so remember the idea here in this course, where we are trying to get you to, is that you will understand how these manufacturing systems perform, So if you get to a system, you can start identifying where are the areas that you can improve. Okay? So we are now focusing on variability. And you know that if you reduce variability, you should be able to improve the performance of your system. So in terms of looking at that from that perspective, we want to be able to find where the variability is in our system. So some of the general strategies are looking for long queues, look for blocking, focus on high utilization resources, consider both flow and process variability, and ask why 5 times. That means that if you find a problem, you start asking, and why is that? And if they give you an answer, you ask again, why don't you get to the root of the problem? Specific targets, equipment failures, setup, are they taking too long? Do you have a lot of rework in your system? That means that there's something wrong with your process. Operator facing, is that the right amount of time that you should take to the operator to complete that? Is that pacing always constant, or do you have different type of pacing during the day? Or anything that prevents regular arrivals and process them. We have one more thing to cover for completing this lecture. And it's a concept of variability pooling. So way to deal with congestions effects is by combining multiple sources of variability. Okay, so the idea here is, can we put together all the sources of variability and try to reduce the variability of our system by considering all of them together? That's the idea in variability pooling. So an example of the use of variability pooling is financial planning. So when you invest in this diversified portfolio, basically you are trying to reduce the risk of not getting enough from your investment. So you're investing in some companies with high risk, some of them low risk. You're combining the risk together, and you should get some type of benefits from it. Okay, so the basic idea is the coefficient of variance of a sum of independent random variables decreases with the number of random variables. So if you have multiple sources of variability of randomness in your system, what the idea of the variability pooling is that if you combine all those sources or random variables together, that would increase your variability in some sense. Maybe because there's some overlapping between some of them, and so on. So as an example, time to process a batch of parts, we have the time to process a single part, the standard deviation of time to process a single part, and we also have the coefficient of variance of time to process that single part. So if we consider, instead of looking to a single part, we consider a batch, which is a group of parts together, we can compute the time to process that batch by multiplying the number of items in that batch times the time to process that single part. And in the same way, the variance, we can compute the variance by multiplying that by n. And the coefficient of variance of the batch is basically the division between this and the square, which is what we have. So the coefficient of variance for that batch will be equal to the coefficient of variance for a single part divided by the square root of n. Okay, so you're combining the processing time of one part into a batch, and that's the coefficient of variance for your batch. In terms of this particular topic, I'm not going to go in depth. Just want to present to you this idea. In my opinion, this is not the best way to analyze systems. I would rather prefer to look at them in individual parts and to be able to identify where the problem is. But this is another idea that's out there and that can be useful, or maybe save you some time and be useful. So that basically concludes the discussion in terms of variability. We have another lecture to start. So I'm going to start now. So let me stop